Hello, everyone. Welcome once again to the Set Theory Seminar. This is our last seminar for this semester, and we will be back virtually in fall. So keep an eye on our schedule website. And today it's great to have back at CUNY virtually Miha Habic. We missed you greatly. And he's currently at Bard College at Simon's Rock. And he will be talking today about some old and new results on non-amalgamable forcing extensions. Go ahead, Mia.
All right. Thank you, Vika. Thank you, everyone, for coming. It's great to be back at the seminar where I grew up. So some old and new results on non-amalgamable forcing extensions. I'm going to tell you what non-amalgamable forcing extensions are. I'm going to tell you what the old results are, and I'm going to sketch some new results that we got recently with some students. Let's see. All right. So everything I present in this talk is joint work with a large set of people. The old results are from a joint paper with Joel Hankins, Lucas Klausner, Jonathan Werner, and Cameron Williams. The paper was sort of interesting because there's sort of a lot in there, and if you take almost any subset of the authors, there's a part of the paper that subset is solely responsible for. Maybe not the empty subset, but and then the new results that I have towards the end are joint with some students here at Simon's Rock, Charles Wang and Kathy Zhang. And it was a pleasure to work with them. And I hope that we can get some more results in the future as well. Anyway, let's get into it, right? The playground for today's talk is going to be this idea of the generic multiverse of a given model of set theory, right? So we're going to fix once and for all a countable model of set theory. May as well be transitive. We don't really need it to be transitive, but it makes life easier. And following Wooden, I believe, we're going to take the generic multiverse of M to be the smallest collection of models containing this M, and then closed undertaking set forcing extensions and ground models of those forcing extensions, right? So if we look at the little diorama here, we have this M. We can take a forcing extension M of G. Maybe M itself was a forcing extension of some ground model N, so we throw N in as well. And then there's other zigzags that you can take. You can go maybe to a forcing extension, into a different ground, into another forcing extension, and so on and so on and so on, right? So everything that you get in this multiverse is somehow produced from M by a zigzag of this shape. We can also just focus our attention on particular kinds of forcing extensions, particular kinds of ground models. For example, we may only care about the Cohen multiverse, so models that are obtained by adding maybe one or maybe many Cohen wheels to M or something like that, right? And that's also reasonable. Okay. So the particular features of the multiverse that we'll care about is the multiverse as a partial order, so ordered by set inclusion. Okay, so we take this multiverse. It has size continuum, right? M was countable. It's not too hard to continue many different models in there, right? It's ordered by subset, and it's sort of surprising that the features of the multiverse, or the features of the multiverse, or rather just the relationship between a model, its forcing extensions, its ground models, compared via set inclusion, wasn't really that prominent for a very long time. At some point since the invention of forcing, the intermediate model theorem appeared, but that was more or less it, right? But then sort of in the early 2000s, work of Reitz and Hampkins kind of jump-started the whole thing. So Reed showed, for example, that depending on the theory of M, the multiverse may or may not have minimal elements, right? This is related to his ground axiom, for example, right? Later on in the initial set theoretic geology paper, Fuchs and Hankins and Reitz showed something about boundedness of increasing chains in the multiverse, right? So specifically, any countable chain in the multiverse arising from a sequence of forcing notions of uniformly bounded size has an upper bound, right? So this tells you something like almost every increasing chain in the multiverse has an upper bound, right? Not quite, because your posets can increase in size so fast that the upper bound would have to be a class extension, but you know. And then the kind of outstanding result of Usuba a few years later, he showed that the multiverse is downward directed, right? So he proved what the geology paper called the downward directed grounds hypothesis. And so we get some actual non-trivial structure in the generic multiverse, because we can always sort of go to a deeper ground, comparing any finitely many grounds that we want, okay? So we'll be interested in studying the complexity of the multiverse as an ordered structure, and specifically our approach is going to be, we're going to try to embed as many partial orders as we can into the multiverse and see what we can do and what we cannot do. And then, you know, the end result is hopefully the multiverse is very complex because many partial orders embed into it. Okay, so here are some easy things we can prove, okay? They don't need any deep thought. First result, any finite poset embeds into the generic multiverse, all right? That's not very hard to prove, right? You take your poset P, you fix mutually generic Cohen reals, C sub P, one for each element of your poset, and then you map your point little p from the poset to this particular Cohen extension of your model M, right? So this is the join of all the Cohen extensions corresponding to the lower cone below little p, right? And if you think about it, I'm going to try scribbling on the slide, so bear with me, right? I'm going to draw my favorite poset. It looks like this, right? What's going to happen is this bottom node is going to go into some Cohen extension MC, and then this node above is going to go into some Cohen extension MCD, and this node is going to go into some Cohen extension MCE, right? And we see that because we took the join over the entire cone, things that are comparable in the poset are going to end up as comparable forcing extensions, and vice versa. If we have comparable forcing extensions, because everything was mutually generic, things had to be comparable in the poset as well. All right. So okay, not too exciting, but you know, in some sense, the project is finished now. Okay, every poset, well, every finite poset events into the multiverse. The multiverse is very complicated. Thank you for coming to my talk. We can push this slightly harder. So the finite poset here can be loosened to requiring just a kind of local finiteness, and then in addition, a size restriction on the poset, right? So the improved version of this theorem is that any locally finite poset of size continuum embeds into the generic multiverse. We need the size restriction because the multiverse itself has size continuum, so you can't hope to embed something larger. What do we mean by locally finite? A locally finite poset is one in which every element has only finitely many elements below it, right? So every lower cone is finite, okay? The way I think of posets like this is, it's just sort of a lot of copies of finite posets sort of side by side and incomparable with one another, okay? How do we embed very large locally finite posets? Well, we want to do essentially the same argument. We want to fix a bunch of Cohen reals. But now we have to ensure that these joins that we have here, that these joins make sense as Cohen extensions, right? So essentially what we want is continuum many Cohen reals so that any finitely many of them are mutually generic, right? And that's, it takes a little bit of thought of how to do it, but it's not that hard, right? In fact, if you think of Cohen forcing for adding just one Cohen real, you can pretend instead of building a infinite sequence of zeros and ones, you can pretend you're labeling the full binary tree with zeros and ones, and then any two branches to that tree are going to give you two mutually generic Cohen reals, right? Because any two branches will eventually split. And once they split, you're building essentially a condition in the product of two Cohen forcings, if you like. I'm lying, but only a tiny bit here, right? Because based on what I said, I get continuum many Cohen reals, but continuum from the point of view of M, whereas I want continuum from the point of view of V, but you can fix that. And I'm not going to say more about that. So, okay, fine. We can embed huge posets. Okay, they have to be locally finite. I'm going to say a little bit more about what happens with infinite posets later in the talk, but a lot of complexity in the multiverse. Okay. Let me just clear everything. Okay. So at the end of the day, though, these embedding results are a little bit boring, right? Because, well, we embedded all of these posets into the multiverse, right? But if I redraw my favorite poset, right? Right, this poset, well, okay, it embedded into these generic extensions, these Cohen extensions, CE, right? But all the Cohen reals here we're taking to be mutually generic, right? So secretly, right, there's a top model on like completing this diamond MCDE, right? That doesn't correspond to anything in my favorite poset over here, right? So we might question, well, can I embed posets into the multiverse, preserving sort of more of the structure, not just the presence of things in the poset, but maybe the absence of things in the poset as well, right? There's something to be said about, well, we know the multiverse to be downward directed, right? So sort of downward features of the poset are kind of prescribed. Not every, we can't really avoid having lower bounds in the multiverse, but maybe we can say something about upper bounds, right? For example, in my favorite poset, these two nodes don't have an upper bound, whereas using this naive embedding, the models do have an upper bound, right? So first of all, we might want to know, does the multiverse support this kind of phenomenon, the lack of upper bounds? Right? So we'll see, maybe that's something, and maybe there's other features in the multiverse that we can exploit by copying other posets, preserving those features. Okay. Let's see. So since we're talking about upper bounds, I'm going to define this notion of amalgamability for models that I want to talk about today. So a family of forcing extensions E is called amalgamable over this fixed ground model M if there's another forcing extension M of G extending each model in E, right? In other words, if this collection of extensions E has an upper bound in the multiverse of M. Right? And so, like I said before, all the forcing extensions that we've considered on the previous slide, everything was amalgamable because everything arose from mutually generic extensions, right? And so the question before us is, can we get instances of non-amalgamability? Right? Can we get forcing extensions that do not amalgamate? Okay. And the answer is that we can, and this seems to be a result that, pops up every 10 or 20 years and then falls into obscurity again. But I believe that while writing our paper, we managed to track down the original reference to it. So I think this is due to Mostovsky from 1976. And he showed essentially, with a caveat, that given M, there are two Cohen reals C and D over M such that M of C and M of D do not amalgamate. Okay. So I can prove this very
Miha?
quickly. Oh, yes.
Just a quick question. So the stuff that you mentioned up to now, where you just want to realize, embed these posets, for that, it doesn't seem to matter that M is a countable model, right? I mean, you, so to speak, you can just write down a forcing that, while here it seems like for this non-amalgamability result, you'd really want M to be countable, right? So that you can construct these specific generics that can't be amalgamated.
Yes, I mean, I sort of agree with you, but I also want to be in a context where, I'm given a model and I have a wide variety of generics available to me in V. Like if you give me an uncountable model, then for all I know, V has no forcing. V has no generics for that model. And yes, I could pass to a forcing extension of V to find all those generics, but I'm really trying to work with a toy model here, and at that point it will be countable. But yes, I agree for these non-amalgamability results, I really need to be able to carefully build the generics, and there the countability of the ground model is.
Yeah, exactly. That was my point. Like it's somehow a different kind of technique that's used all of a sudden, where you really construct the generics rather than just saying, okay, I force with this poset and there's the generic. Right. Yeah. Okay.
Yeah.
So maybe can I interrupt too? You can do some of these constructions if your model has like the right closure stuff and you're doing co-enforcing at larger cardinals. You can do a similar sort of construction. It doesn't have to be countable.
Right.
It's just, like Miha said, countable ensures you get the generics.
Right.
Right.
Yeah, but I mean, I guess what I mean is like, okay, yeah, you can construct them, but you could just say, okay, let's pass through a forcing extension where they exist, but then you don't have control over what they will be like. Exactly, right? Yes. Okay, anyway, yeah.
It's sort of interesting. I remember asking him a math overflow question many years ago, where I essentially asked about this distinction, because in most arguments that we as set theorists see every day, we do some forcing and we don't particularly care about what the generic looks like. We just take some generic and that's fine. But sometimes for what I'm talking about today, and maybe for other applications as well, sometimes you really need to carefully build a very specific generic to do what we need to do, right? And so we're going to see examples of that, I guess. All right, so how do we build these two non-amalgamable Cohen wheels? Well, what we're going to do is we're going to fix what I'm going to call a catastrophic real called Z for M, right? What is a catastrophic real? It's a real that M is really not allowed to see ever without something really terrible happening, right? For example, Z might be a real coding the ordinal height of M or something like that, right? At the very least, what I want is that Z doesn't appear in any forcing extension of M, for example, right? If M doesn't have 0 sharp, then 0 sharp would work, or anything like that. Okay. I'm going to say a little bit more about this afterwards. But okay, so we fixed this catastrophic wheel, and then we're going to build two Cohen wheels, as two rows. How do you build Cohen wheels? Well, you have a conveyor belt. The conveyor belt serves you dense sets. You need to meet those dense sets, but you're going to do something else also, right? So, okay, C needs to be generic. So you get a dense set, you meet this dense set in the C row, and you let D be inactive for this entire time, okay? So these blank cells here in the D row mean that you just put zeros everywhere here, okay? And then you put a column of ones, and then you put a column coding the first bit of your catastrophic real Z, okay? And that's sort of the first step of your construction. And then you say, well, D also should be generic. So you need to give D a chance to be generic. So you let D meet a dense set. You let C be inactive for that entire time. So you put zeros in these blank cells. You put a column of ones, and then you code the next bit of Z. Okay, and then you keep going back and forth like this. You let C be generic a little bit. You let D be generic a little bit. You put columns of ones to serve as a kind of coding marker, and then you code bits of Z, going on and on and on and on, right? And if you think about what happens after you're done, well, C and D both met all of the dense sets that they needed to met, so C and D are both Cohen wheels separately. But if you take C and D together, the only time you see a column full of ones in there is when you put it there explicitly as a coding marker, and then it's followed by a bit of Z, right? Because in the what you might call the genericity steps, one of the rows was always inactive, always had zeros, while the other one was doing whatever it needed to do to become generic. All right. And so at the end, you have these two wheels. Their join computes Z in a very simple way, right? So both of them together cannot appear anywhere in the multiverse of that. Okay. All right. Okay. So this is a prototypical construction in which forbidden information is somehow hidden between several generic objects in such a way that all of them together can recover it. And Mostovsky used it to essentially prove an embedding theorem for posets like we had before, except that now the language of the ordering is augmented with a non-amalgamability predicate, right? So this is, again, closer to what Mostovsky proved, again, with a tiny caveat. So fix a finite L and let A be a family of subsets of this index set containing all singletons enclosed under subsets. And the way we think of this script A is the elements of script A are exactly giving us the sets of indices whose corresponding extensions should be amalgamable, right? So what we prove is that there are Cohen wheels C0 through CL such that for any subset of the index set, the family of these Cohen extensions MCI for I in A is amalgamable if and only if this A is a good set. So A is in this family of subsets that we specified. All right. And so these requirements on script A exactly correspond to what should be a consistent assignment of amalgamability and non-amalgamability, right? All singletons obviously should amalgamate with themselves. And if a large set of extensions amalgamates, then any subset also amalgamates, obviously, right? Okay, and I can draw another picture for how we prove this. Well, it's similar to before, right? We need to give certain collections of extensions a chance to become amalgamable. We're going to ensure amalgamability by actually making those extensions mutually generic. Okay, so I turned the picture by pi over 2, I guess. So now the wheels are going to grow in the columns. All right, each column corresponds to a particular index between 0 and L. All right, and so at a particular step, we need to give a set of columns given by an element of script A, a chance to become mutually generic. All right, and so we do that. Okay, we meet a dense set here. All the other columns should be inactive during that time. So all of these blank spots are filled with zeros. And then we code a full row of ones across the entire thing. And then we code the first bit of a catastrophic real. And then we do it again with a different collection of columns that should eventually become amalgamable. Okay, and then we code a full row of ones, and then we code another bit of Z. And then we do it again, and then again, and again. We can see, I guess, in this situation, the sets of columns started to repeat, right? These active columns are the same as these active columns. These active columns are the same as these active columns. So we're going to go back and forth. We're going to cycle through all of the requirements we need to meet in terms of both the dense sets and the sets of columns that need to become mutually generic, right? And then again, for the same reason as before, if we have a set of columns that is not from A, right, that means that, in particular, because script A was closed under subsets, that means that that bad set of columns isn't covered by any set in script A. And that means that if I look at those, columns, I'm going to get, in each step of my process, I'm going to get at least one column that was inactive, right? It was never the case that all of those bad columns not from script A were active at the same time. And that means that the only time I can get a full row of ones across all of those bad columns is coming from these coding steps here, right? Is when I explicitly put a coding marker across all of the columns. Okay, so we get non-amalgamability that way. All right. And so the corollary of that result, I mean, you know, Mostofsky proved it for these families of subsets of an index set, but very easily we can get that any finite poset now embeds into the generic multiverse in a way that preserves non-amalgamability, okay? And essentially, what we need to show for this is just to show that any finite poset embeds into a family of subsets in such a way, right? And then we can apply Mostofsky's theorem, right? And essentially, this is just the cone idea from before, right? We're going to map each point from the poset to its lower cone, and then close this family of cones under subsets, and we get exactly the kind of family that Mostofsky can deal with, right? I have a little caveat here for people, mostly for Cameron, that Mostofsky actually wasn't interested in cone wheels. He was interested in second order set theory, and essentially he wanted complicated families of models of second order set theory with the same first order part, but different second order parts, so that you couldn't amalgamate the second order parts. And so he didn't add cone wheels, he added Cohen subsets of Ord, but essentially this was the proof. All right. So, okay, this was 1976. Okay. It was actually interesting because I think Cameron found this result due to Mostofsky, and it had some kind of weird reference in a conference proceedings. And I happened to be at Charles University in Prague at that point, and my office was in the sort of departmental library, and I was just sort of pacing up and down my office, and I looked at a random shelf in the library, and I found those proceedings. So finding that reference was surprisingly easy. Anyway, so okay, we have this result. We want to strengthen it now in a variety of ways, right? So here's what we might want to do now that we know how to get non-amalgamability. We want to have control over lower bounds as well. Okay, so let me say what I mean by control over lower bounds. I'm going to draw my favorite poset again. Here's my favorite poset. Okay, we know how to embed this now into something that looks like M, and then here's MC, and here's MD. All right, and these two do not amalgamate, just like these 2 points in the poset don't amalgamate. Okay, that's wonderful. But there's something else in this poset. In this poset, these 2 nodes have a meet that's this lower node here. Okay, if I'm not particularly careful with how I built my generics, I could very well realize this poset in such a way that these 2 non-amalgamable Cohen extensions have a meet that isn't exactly M, but is something else living above here. All right. And maybe I want to avoid that. Maybe I want to specify, oh, I want to look at posets with a clearly specified least element, and I want that least element to go to M, and then I want meets, if they exist in my poset, to sort of embed nicely into meets of, or I should say intersections of my forcing extensions in the multiverse. Okay, so maybe I want to achieve that. Okay, so that's one thing. I'm obviously interested in seeing what I can do with infinite posets. Can I embed infinite posets into the multiverse while dealing with non-amalgamability, lower bounds, things like that? And also, maybe I want to not just deal with co-enforcing, right? If we look at how this coding worked, it was kind of specific to how co-enforcing works, right? Obviously, you know, I'm building these generics. I have some columns. I have cells with zeros and ones. You know, I have the specific coding marker. I would need to think a little bit about how to make this work for other forcing notions. Right? And so,
could I just make a comment? I think it's interesting because these two requirements about preserving the non-amalgamability and also lower bounds, there's a tension between them, right? Because it's very easy by picking mutually generic reals to arrange that the intersection is going to be the ground model,
yes.
But then you also have an upper bound. So
yes,
it's interesting.
So there's an interesting tension between the two. Yeah.
Cool.
All right, so I have things to say about all three of these points. So let's see what we can do. All right, so I'm going to define a better kind of embedding that will kind of take care of essentially the lower bound business for us. Okay, so let P and Q be posets with least elements called 0. And we're going to call a map F from P to Q a star embedding if, first of all, it's an order embedding, right? And second of all, if you give me a finite subset of P of the domain, that X is going to have an upper bound if and only if its pointwise image does, and it's going to have a non-zero lower bound if and only if its pointwise image does. Okay, so the upper bound thing is exactly the amalgamability part. The non-zero lower bound goes towards this, you know, I want intersection, you know, I want interesting intersections to be preserved in some sense. Right? I don't want to create models that have too big of an intersection, for example. All right, so let's get right into it. Okay. What can we do with lower bounds? Well, we essentially get the exact same theorem with as Mostovsky had, with this additional lower bound requirement, right? So if I take a finite index set, A is a family of subsets of this index set containing all singletons closed under subsets, just like we had before, then we can find Cohen wheels indexed by the same index set such that the following three things hold, right? So if A is a good set of indices, so if it's supposed to be amalgamable, then the Cohen wheels are going to be mutually generic. That's nice. If B is a bad set of indices, if it's not supposed to be amalgamable, then the forcing extensions don't amalgamate. And in terms of lower bounds, if I have two good set of indices and I look at their corresponding Cohen extensions, the intersection of these Cohen extensions is going to be, essentially, this is saying the intersection is as small as possible, right? It's exactly the forcing extension given by the Cohen wheels that they both have in common. Okay. All right. So essentially, what we're doing here is we're building these Cohen wheels. We're trying to code information into these Cohen wheels, but we're trying to not code too much information, right? So that we're trying to keep the intersection small, right? And as a corollary of this, I'm going to say a little bit about the proof of this theorem in a minute, but as a corollary of this, we can see that any A as above, so any family of subsets, star embeds into the generic multiverse. And as a consequence, every finite partial order star embeds into the generic multiverse. Okay, so that's sort of exactly what we wanted. It's giving us features of the multiverse where any pattern of amalgamability, non-amalgamability, well, let's say any finite pattern, plus any pattern of interesting lower bounds or not, can be realized. All right. So let me talk a little bit about the proof of this. I don't want to take too long. What we want to do is build the generics as before, as columns in this matrix. We want to make sure that columns are only simultaneously active at coding points, right? Meaning where I'm going to code a whole, where I'm going to put a whole row of ones across the entire matrix to signal that a bit of Z is coming, a bit of the catastrophic real, or potentially if the columns should be amalgamable, right? So if I'm meeting some dense sets, then possibly I'm going to have ones across a whole set of columns, okay? And so just like before, the construction will sort of have three types of steps, right? There's going to be the genericity steps, where we give the columns above some good set of indices a chance to become generic, all right, meeting a dense set. We're going to have coding steps, where we code a bit of Z across all of the columns. Okay, so that's just like before. We put a row of ones and then a row of the next bit of Z. And then there's the intersection steps, right? That's sort of the added complication here, where, like we said, we're trying to keep the intersection of two forcing extensions to be as small as possible. And the way we're going to do that is, if we're given one Cohen named sigma and another Cohen named tau, each one corresponding to different sets of columns, we're going to try to force these two names to be different, all right? So, okay, since this intersection step is the new thing, I guess, I might say a little bit more about how this happens, right? How we force these two names to be different, right? So the idea here is going to be that what we're dealing with really is a big product poset, right? It's this big Cohen forcing, right? And we're going to be able to kind of manipulate our conditions so that, one name gets decided this way, another name gets decided another way, and maybe if they get decided the same way, we fix the condition a little bit and something will happen, all right? So the key idea here is this notion of what we call a J strengthening of a condition, right? So let's say that I have P and Q, two product conditions with index set I. The support of the conditions doesn't really matter. Maybe I'll say a little bit later about when we care about support and when we don't care about support. And let J be a subset of the index set, right? And so we say that P is a J strengthening of Q if P is a strengthening of Q, first of all, but the strengthening only happens on coordinates in J, right? So P restricted to I minus J is the same as Q restricted to I minus J, right? So if I draw, scribble what this kind of looks like, right? Here might be P, he might look like this, right? Here are some columns in A. Here are some columns in A prime. Oh, sorry, I should have J and J prime, J, sorry. I'm jumping ahead. Here's J. If we want to strengthen, if we want a J strengthening, well, I can strengthen, but I only strengthen here over J, and nothing happens away from J, right? And so this would be a J strengthening. All right. So why is this useful? Well, we have this key lemma that's going to essentially tell us, it's going to give us names that will allow us to force two things to evaluate two different things, right? So let's say I have two index sets, J subset of I. Let's take posets indexed by the big index set. And let's take the product over of all these P sub i's using whatever support again. And let P sub j be the subposet with supports, or with the supports of the conditions restricted to j. Okay. So then we take chi, a big product name for a subset of V of G restricted to J. So it's a big product name, big forcing name for a subset of the sort of small forcing extension, all right? And let's suppose that this name is forced to not be an element of the small extension, right? So it's a subset, but not an element, okay? Then the lemma says that you can find a PJ name row such that no J extension of Q decides whether rho is in chi or not, okay? Now this is pretty general, but the intuition that I want to leave you with is, think about what happens if J is the empty set, okay? If J is the empty set, okay, then we're looking at P sub J is the subposet with supports restricted to the empty set. That's nothing really, so that's the trivial poset. Chi is a name for a subset of V, G restricted to J, that's just V. And suppose that chi is forced to not be in V, right? So essentially, chi is a name for a subset of the ground model, but not an element of the ground model. So more or less, it's a name for a new set of ordinals, if you like, okay? And so then what this lemma is saying, there's a PJ name, aka a check name, such that no J extension of Q decides whether rho is in chi. If J is the empty set, what is a J extension? Well, you're only allowed to strengthen on J. If J is the empty set, you're not allowed to strengthen at all. So the only empty set extension of Q is Q itself. So what this lemma gives you is that essentially, if chi is a name for a new set of ordinals, then you can find a check name for an ordinal so that Q does not decide whether rho is in chi or not. Okay, and that should be relatively clear, right? If Q decided whether every check name was in chi or not, then chi would be in the ground model because you just look at what Q decides. Okay, and essentially this lemma is a generalization of that, where you're allowed to have this intermediate extension VG restricted to J. Okay, all right. So let's clear everything. So let's see how this lemma gets used. To be brief, you're in your construction, you're building your Cohen generics, you've built a condition P up to now. You're given two sets of indices, A and A prime. You're given an A name sigma and A prime name tau. And again, for simplicity, just to not have to think too hard, we're going to assume that A intersect A prime is the empty set. Okay. So what we need to do is we need to prevent these names from evaluating to the same set from the same to the same set, not in this M, extension corresponding to the intersection of A and A prime, aka the ground model, right? Because if you think about it, how are you going to check? How are you going to check whether the intersection of M of C sub A and M of C sub A prime is the correct model? Well, you're going to take an A named sigma and A prime named tau, and you're going to see, oh, do they both name something in the do they both name something that isn't in the ground model or not? Okay, so in that situation, I need to get them to, if they do evaluate to the same set, I need them to also come from the ground model. Okay, so again, for simplicity, I'm going to assume that both of these are names for sets of ordinals. Okay, and then I have sort of two possible things that can happen. Either the condition I've built so far forces that one of these two names is already in the ground model. And if that happens, then I'm fine. Because if one of them is in the ground model and they happen to evaluate to the same set in the extension, okay, then they're both in the ground model and I'm fine. Okay. The problem is if both of them don't evaluate to something in the ground model and they happen to be the same. Okay. So otherwise, I'm going to find an A extension P, which forces that this first name sigma is not in the ground model, and I'm going to apply the key lemma. Okay, and so the key lemma gives us a name rho such that this P prime doesn't decide whether rho is in sigma or not. Okay, and then I'm going to take another A extension to decide whether rho is in sigma or not. Okay, but then to prevent something bad happening, I'm going to need to pad the condition I have with zeros, because whatever I'm doing, I need to prevent unintentional coding from happening. I need to keep certain columns inactive in what I'm doing right now. So let me draw a picture, and I apologize that I'm drawing over the text, right? But bear with me. So, okay, here's a condition that I've built. Here's P, and here's A, and here's A prime. Okay, and what I've done so far is I've taken an A strengthening here. I call this P prime. okay? And this P prime has now decided whether rho is in sigma or not, okay? Oh, sorry. Let me put it this way. I found P prime. P prime hasn't decided whether rho is in sigma or not. I take another A extension to P double prime to decide whether rho is in sigma or not, okay? But now, because I don't want things to be active across the whole thing here, I need to put a bunch of zeros everywhere here. Okay, in particular across A prime. Fine. And I call the resulting thing P double prime. So now I sort of have two things that can happen, right? It could be that, you know, I decided whether, let's say that I decided that rho is in sigma, okay? It could be that what I've built so far decides that rho is not in tau. If I've done that, then what I've built is wonderful because this whole condition now forces that sigma is not equal to tau. Great, okay. I've forced these two to differ. I forced them out of the intersection of MCA and MCA prime, okay. But if that doesn't happen, right, then by adding these zeros here, I may have inadvertently forced that rho is in tau, okay, which is unfortunate because now I haven't yet ensured that sigma is different from tau, okay. So what do I do now? Well, I need to kind of roll back my construction and make up for my past sins, right? So what I'm going to do is I'm going to keep these zeros here, but I'm going to erase this part of P double prime up above here, okay? So what I have, what I have now is a bunch of zeros here over A prime, but over A, I just have P prime. And remember, P prime was given such that P prime did not decide whether rho is in sigma or not. Okay. And because both, well, rho is a check name and sigma is an A name, that means that now I can extend just involving columns of A to something else above here that now decides rho and sigma differently than rho in tau was decided, right? So I can extend now over A to force that rho is not in sigma, okay? Whereas I haven't touched whether rho is in tau or not because this was all decided on this A prime part, okay? So now I've kind of reconstructed my condition and I've ensured that sigma is forced to be different from tau. They differ on this rho bit. And now I can continue with my construction, right? I've ensured the intersection will stay small, and I can go back to my genericity steps, to my coding steps, whatever else I might need, okay? The only thing you might care about is if A intersect A prime isn't empty, so if there's something in the middle here, then you shouldn't erase everything from A. You should keep the zeros on the part of A intersect A prime. All right, but then the key lemma is good enough that it still lets you fix the part just over A without touching the part over A intersect A prime, and it's still okay. Okay, so let me clear this, and let's sort of move on. Okay. All right. So this essentially, that was kind of a glimpse of what goes on into this, ensuring that the intersections are kept small and that we get this star embedding. Okay. Now let's talk a little bit about what happens with infinite posets. Okay. And it turns out that the above proof generalizes pretty readily to partial orders of the following form. Okay. So we'll still be working with families of subsets of a particular index set, but we require these families of sets to have what we call the finite obstruction property, meaning that if you have a set B not in your family, there's a finite reason why it's not in the family. There's a finite B prime subset of B, which is not in this script A, okay? If you think about it, this is kind of a compactness property of this family script A, okay? And we get a direct generalization here of our theorem. So if script A from M is a family of subsets of a set I, possibly an infinite index set I, and this family contains all singletons, is closed under subsets, it has the finite obstruction property in M, then there are Cohen wheel C sub I with exactly the same properties as before, right? So essentially what we proved is that any family of subsets of an index set I with the finite obstruction property star embeds into the generic multiverse exactly in the way we had for families for subsets of finite sets. All right. Let me maybe skip this slide. All I want to say about this is you might say, well, you know, what is this compactness property really talking about? What is this finite obstruction property really saying? It turns out that this is pretty close to being a sharp result in the sense that if we strengthen our notion of embedding a little bit to what we call a strong star embedding, we can prove that if a family of sets strongly star embeds into the Cohen multiverse, then that family must have the finite obstruction property, all right? So this theorem here is, in a sense, close to being sharp in terms of what things you can star embed into at least the Cohen multiverse. Okay, and this sort of relies on an earlier version of the Hampkins-Reitz Fuchs result that I stated earlier about upper bounds for increasing chains in the generic multiverse. But anyway, let me skip this. Okay, so let's say something about what happens with forcings that aren't just Cohen forcing. Okay, so we can't expect to achieve non-amalgamability without restricting the posets in some way, because there's this phenomenon where certain posets automatically amalgamate their extensions because any two generics are automatically mutually generic, right? So as an easy example, if you take any two generics for adding a Cohen wheel and adding a Cohen subset of omega 1, these two will be mutually generic, right? Because, you know, the omega 1 forcing is countably closed. It doesn't add any dense subsets to the Cohen wheel forcing. So any old Cohen wheel will stay a Cohen wheel. For a more interesting example, you can look at Suslin trees that are Suslin off the generic branch. If you take any two branches through a tree like this, right? Well, the first one is generic. The second one eventually veers off of the first one, but the tree off the first branch was Suslin, right? So the second branch is also generic, right? So the two are mutually generic. And so on and so on and so on, right? You can kind of list examples like this forever. But a class of forcings that's pretty rich, but still exhibits a non-amalgamability phenomenon are, I think, something Joel isolated, these things called wide posets. And we call a poset wide. A poset P is wide if there are antichains of size cardinality of P below any condition, right? So a way of thinking about this is these are the posets that have terrible chain conditions, right? Anywhere you look, there's just no non-trivial chain conditions to be found, okay? So examples of this are, okay, Cohen forcing for silly reasons, but also collapse posets, Sachs forcing, Matthias forcing. You know, if you like forcings that add reals, all of these things that you need the theory of proper forcings to work with, all of these will tend to be wide, for example. Right? Okay, the theorem here ends up being pretty much, again, almost a direct generalization to this new class of posets, right? So let's take a family of wide posets, P sub I. We require them to all be the same size in M. And we let script A be, again, a family of subsets of the index set as before with a finite obstruction property and so on, and so on, and so on. Then we can find generic filters for all these posets with all the same properties, right? If A is a good set of indices, then all of these generics will be mutually generic. If B is a bad set of indices, the corresponding generic extensions will not amalgamate. And if A and A prime correspond to 2 extensions in this embedding, then intersections are as small as possible, right? Okay, I'm not going to go into the proof of this really because it gets really annoying, right? But you can imagine that at least in the basic outlines, the idea should be the same, right? You're trying to build some generics. You have your conveyor belt feeding you dense sets. You have your catastrophic wheel that you need to code somewhere, right? You have some intersection steps where you need to make sure that the intersections of your generic extensions don't become too large, right? And really the only thing that is different from what we were doing before is the coding steps, right? Because as we said before, these aren't coding conditions anymore. We're not building a matrix. We can't just put ones across everything. What does that even mean? Okay. So instead, here's where we rely on this idea of wideness. Okay. So because these posets are wide and they all have the same size, we fix for each condition in each of these posets a large maximal anti-chain Z of P below this P, okay, in order and enumerated in order type kappa, okay. So the idea is that if you look at a condition like this, and you have a generic G sub I containing this condition, this generic is going to pick out a single condition from your maximal anti-chain ZP, okay. Now, we enumerated this maximal anti-chain, so essentially this generic picks out an ordinal below kappa. Okay. If we were doing this naively, you might say, well, okay, all I need really is to code zeros and ones because I'm going to code the bits of my catastrophic wheel. Okay, so why do I need kappa, kappa much space to code here? And the reason is that, okay, fine, you can code a bit, but then you sort of quickly realize that because this isn't just co-enforcing, you need a way to keep track of the coding points, right? So these conditions whose maximal antichains you're going to consult in order to find where the next bit of your catastrophic wheel is coded, okay? And it's not quite as simple as like, looking for, oh, I started with this condition, and then I looked at its maximal antichain, and then I look at this next condition in that maximal antichain, and then I go further and further and further, because there might be strengthening happening in the genericity steps and the intersection steps, and all sorts of things can happen, okay? So in your coding step, you're going to code not just the catastrophic wheel, but you're going to code essentially the entire history of the construction up to now. So you're going to code all the coding points you've used so far, plus in addition, more or less, you're going to code the next coding point you're also going to use, okay? Plus some additional information that's going to let you decode this entire history from an arbitrary bad set of indices, okay? So this is essentially the reason why we need so much space for coding, why we need these posets to be wide, is because I need to code not just a 0-1 bit, but I need to code a sequence of conditions in all of my posets, right? And the posets all have size kappa, so I need to code things. I need kappa much space to code everything. Okay. But again, I'm not going to go into details. It's kind of a pain, but okay. So what do we have now? Well, we have these star embeddings. We know how to embed these infinite families of subsets of an index set. We've isolated this finite obstruction property that's close to being sharp in terms of what we can star embed and what we cannot star embed. And we have this result on wide posets, which gives us a lot more richness in terms of what forcing extensions we can create, right? Where we can find this non-amalgamability phenomenon, okay? But still, there's this nagging feeling that, there's posets that we really like that aren't covered by this general wide version of the theorem, right? There's CCC posets that are just too large to, be wide. And so we might wonder, can you say anything about non-amalgamable extensions for these, very popular posets, right? So I'm going to say something a little bit about that. So let me say, this is where the cutoff happens. What I've been talking about up to now is from our paper with Joel, Cameron, Lucas, and Jonathan. And this now is what I did with Charles and Kathy, right? So our main examples that I'm going to bring up today are heckler forcing and then a flavor of Matthias forcing. Okay. So heckler forcing, a quick recap. A heckler condition is a pair, S comma E. S is a finite stem that's trying to grow into a real. E is a finite collection of functions, omega to omega. All right. And the generic real that you're trying to add is a real that's not dominated by any ground model real, right? So how do you strengthen a condition? Well, you can grow your stem. You should grow your stem S in such a way that you get above all the functions you have in your side condition E, and then you're allowed to grow your side condition E as well. You're allowed to make more promises about what you're going to get above in the future. Okay. Heckler forcing is incredibly CCC, but it's also a large poset, thus it's not wide, right? Its antichains are too small. Okay. And so you might ask the question, how complex is the Heckler multiverse? You know, can we get nonamalgamability? Can we star embed interesting things and so on? And it turns out that we can, and the results are essentially the same as for the Cohen multiverse for, you know, reasons that aren't too surprising, right? In fact, right, any Heckler extension contains a Cohen extension, because if you look at a Heckler real and you look at it mod 2, you get a Cohen real, right? Because, you know, to meet a dense set with a Heckler condition, you know, you need to, you know, get above some finitely many functions, right? But, you know, Heckler forcing doesn't care if you get above them, you know, using odd values or even values, right? So in addition to strengthening the Heckler way, you can also do whatever you want in terms of mod 2, so you can strengthen to whatever Cohen condition you like. Okay, so you can meet dense Heckler sets while also meeting dense Cohen sets at the same time. So the same kind of coding will work as did for the Cohen results, right? So we get exactly the same kinds of embedding theorems. Any family of sets with a finite obstruction property will star embed into the Heckler multiverse. Okay, so this turned out to be not particularly surprising, but let's move on to a version of Matthias forcing, right? So let's fix a filter F on omega extending the cofinite filter, okay? And we're going to define a poset M sub F with conditions pairs S comma F. S is, again, a finite stem that's going to grow into a subset of omega. And F is an infinite element of the filter that lives above the max of the stem. Okay. And the way you strengthen your condition, you make your stem longer by adding elements of your upper part F to the stem. And then you're allowed to shrink the upper part to a smaller infinite element of the filter. Okay. So ordinary Matthias forcing uses the improper filter, just the whole power set of omega, and this forcing is wide, right? It has size continuum, it has antichains of size continuum. So we know how to deal with it with the wide version of the embedding theorem, right? On the other hand, if F is a proper filter, then this filter-based Matthias forcing becomes very CCC again, okay? And so we might wonder, what can you say about this filter-based Matthias multiverse, okay? And I should say, since the Heckler result was a little bit disappointing, it is known that this filter-based Matthias forcing may or may not add Cohen reals depending on the exact nature of the filter F that you use. I forget what the exact characterization is. It has something to do with F being maybe a p point or something like that. But I forget, but a characterization I think is known exactly when M sub f adds a cone wheel or not. So, you know, in the unfortunate case that we don't add a cone wheel, we're going to need a different kind of coding to possibly get non-amalgamation between these kinds of Matthias extensions. But we can get a coding like that, okay? So we can prove in an analogy to Mostovsky that there are, fix whatever filter f you like, there are M sub f generics xy over M such that these two extensions do not amalgamate, okay? And so the proof is, again, you know, we're going to code a catastrophic real. I wrote down what I want to do here, but I think it's better for me to draw a picture again. So let me draw a picture. And let me show you how we code a bit of Z into our generics, okay? So I have two Matthias conditions, right? Here's a stem. Here's an upper part. Here's another stem. Here's another upper part. Okay. Okay. First, remember we needed to give both of these two things, both of these two conditions, a chance to grow into a generic, right? So we need to meet a dense set. Okay, fine. We meet a dense set on the first condition side by strengthening the stem a little bit and then extending the upper part, and then making the upper part smaller. Before we give the second condition a chance to be generic, what we're going to do is we're going to shrink the upper part of the second condition first. And we're going to shrink it so that it lives completely above this extended stem of the first condition, okay? And then we give the second condition a chance to become generic. So we extend the stem a little bit and we get an upper part. And then we do the same thing on the other side. So we shrink the upper part again to live above the second part, the stem of the second condition, okay? So notice what we've done now is we've extended the stems of the two conditions that we have in a way that doesn't intersect, right? The two stems are completely disjoint, except for the possible intersections we have from what we've built so far, okay? And now for the coding part, remember that these two upper parts of the two conditions come from a common filter, okay? This is a proper filter. All of its elements are infinite. So in particular, these two upper parts intersect. So what we're going to do is we're going to add a point to the stem, the same point to the stem of both conditions, all right? So we're going to add an intersection to the two stems. That's going to be our signal that some coding is happening. And then I need to code either a 0 or a 1 bit coming from the catastrophic real Z. And I have a few different ways of doing it. An example of how we might do it is if I want to code a 0, I also add the next point of the intersection immediately to the stems. So that if I look at the stems, they intersect at two adjacent points. Or if I want to code a 1, instead of adding a point of intersection immediately after, I add something to the stem of the first one, I add something to the stem of the second one, and then I add another point of intersection. All right. So the way I'm going to, I keep doing this over and over again. These two conditions are going to grow into generics, okay? And the way I'm going to decode the catastrophic real Z from them is I'm going to look at sort of pairs of where the stems or where the generic subsets of omega intersect, okay? And I'm going to see, oh, do these intersections happen one right after the other, or is there a little bit of space in between them? And I'm going to decode a 0 bit or a 1 bit from that, depending on what happens. This coding technique is sort of very closely related to this notion of oscillation that Todorcevich has for, a much more general setup, but right here we're using it just to code a simple wheel between two Matthias generics, essentially. Okay, so let me clear my doodles. And so essentially using this new coding idea, we can feed that into the general machinery of what we had before. to reprove the same star embedding theorem, but this time for this filter-based Matthias multiverse, right? So A is another family of subsets of a given set I, finite absorption property. F is a proper filter on omega extending the cofinite filter. Then there are Matthias generics X sub I over M with, again, all the same properties, right? The correct ones are mutually generic. The incorrect ones do not amalgamate. And then the intersections of the generic extensions I get from this embedding are as small as possible, right? And the proof, like I said, works exactly like in the coding case, except that now we use this new coding method, right? And the key lemma, again, comes into play at the intersection steps. All right, so what happens next? All right, well, these embedding results tell us something about the complexity of the multiverse, right? Number one, they tell us that there's local complexity since any finite pattern and some infinite patterns can be found in the multiverse, right? So locally speaking, it can look as crazy as you want it to look. But on the other hand, there's global simplicity to the multiverse because it's so easy to find whatever pattern you want to realize. You know, you just, if it's not where you're looking, you just need to look somewhere else, you know, to find whatever pattern you want, right? So as a corollary of these embedding theorems that we have, we can show that the exist theory of the set generic multiverse with this subset relation, and possibly if you want also non-amalgamability predicates and a meet predicate, this theory is decidable, right? How do you decide it? Well, it's very easy, right? Like what is an existential statement about the multiverse? Well, it says, well, there exist some models that are ordered in this particular way, and some of them are amalgamable, and some of them are not amalgamable, and some of them are meets of the other ones, and so on and so on and so on. But, you know, based on what we've just seen, you just need to check all the requirements, that all the requirements are consistent for a partial order, essentially. And then if they are, you just say, yes, I can realize this, I can embed this, I can star embed this somewhere in the multiverse, okay? If you want to take the next step though, right, going to adding another quantifier, things become kind of difficult, right? So if you think about wanting to decide a for all exists statement about the multiverse, right, that's saying something like, for any given pattern that you've already realized, there are some models that interact in a particular way with things that you've already realized, right? That's some kind of extension of embeddings property that you want, right? So this is our question. Given posets P contained in Q, with P sitting nicely in Q, you know, if two things are not amalgamable in P, but they become amalgamable in Q, you're going to have trouble. And you have a star embedding of P into the multiverse. Can you extend this star embedding to embed all of Q, right? And it turns out that this is quite difficult, right? When I first started thinking about these questions about amalgamability and non-amalgamability and extent and, you know, building these embeddings, I think the naive thing to try is to be like, well, okay, I can realize some very small patterns. How am I going to realize larger patterns? Well, I'm going to do it inductively. You know, I realize a small pattern and then I add another point that realizes a particular type with the points I already have. And then I add another one, and then I add another one, right? And I at least could never get that to work, right? Because this is exactly trying to solve this extension of embeddings problem, right? We do have some very, very partial results for the Cohen multiverse in this direction. Right, so the first one is kind of trivial, right? Given countably many Cohen wheels in whatever relationship to one another, there is another Cohen wheel which amalgamates with all of them, right? Just take one that's very, very generic over everything you've built so far, and it's going to amalgamate, right? Something slightly less trivial, but still not too hard, is if you give me any Cohen wheel, I can find another Cohen wheel which does not amalgamate with the first one. Okay, so this is an instance of extension of embeddings where you go from a one element poset to a two element poset. Okay, and this is more or less what I know how to do, right? Like you can kind of bootstrap this a little bit, but it gets very difficult very fast, okay? If you have experience with computability theory, these questions are very much related to questions that people have asked about the Turing degrees, right? And for Turing degrees, we know the answers to this, right? Like there is, there's a characterization of when you can extend embeddings and things like that. Obviously, the Turing degrees are a different structure from the generic multiverse. You know, there's joins of Turing degrees, everything amalgamates somewhere, whereas, you know, we get non-amalgamability into generic multiverse, but still I think there's close parallels that we should try to exploit, I guess. Anyway, and then some final questions based on other types of forcing extensions that I would like to know more about. A forcing notion that's conspicuously absent from everything I've talked about so far is random real forcing. I know very little about random real forcing. I have no idea how I might try to code anything into random reals, right? So I would really like to know if this non-amalgamability phenomenon also arises in the random generic multiverse. I think it's very likely that it does. I don't quite know how to get there. Okay. And then the second question, I think, is a good student question. This is the question I started my students with, and then you couldn't really get anywhere, so then we did something else. But so I would like to know if there's a straightforward way to do some kind of coding scheme for silver forcing. So if you don't know, so silver forcing is kind of like Cohen forcing, so you're trying to add a real, but instead of finite conditions, you have conditions that are co-infinite. So you're allowed to specify infinitely many bits in your condition as long as you leave infinitely many of them blank, okay? And it seems likely that you should be able to have some kind of straightforward way of coding a catastrophic real Z into your silver conditions as you try to build a silver generic. You know, I should say silver forcing is wide, so we know how to deal with silver forcing, at least abstractly, right? But the coding we had for wide posets is not transparent at all, right? It's something weird is happening, and you have to enumerate anti-chains, and who knows what's going on. It would be really nice if we could have a way of coding into silver generics that was more similar to what we did for Cohen forcing, where, you know, something is active, something is not. You code a bit of Z, you meet some more, you become a little bit more generic, you code a bit of Z, and so on and so on and so on. All right, anyway, I think that's all I have for today. Thank you very much for your attention, and if anyone has any questions, I'm happy to answer them, or try to answer them, I guess.
I have a comment. And that is that you said Mostovsky in 1976, but he died in 1975.
Oh, that's interesting. So I think the reference is from logic colloquium proceedings or something like that. So I guess what might have happened is that he attended his last logic colloquium and his paper made it into the proceedings, but he passed before the proceedings appeared. But that's interesting. I didn't realize that.
He died of a heart attack in Vancouver.
Oh, okay. That's interesting.
I'm a stash now, but I enjoyed your talk. Thank you.
Oh, thank you.
Yeah, Miha, thanks very much. Great talk. Anyone else have questions, comments?
So I should know the answer to this, but I don't. Are there any known natural classes of forcings where you provably don't have this non-amalgamability phenomenon? Like any two forcings in the class will always amalgamate? I guess what I'm asking, because you want to prove this, for random real forcing, for example.
Right.
Are there any cases where this doesn't happen?
I don't know off the top of my head that there's a nice, something you would call a nice class of forcing, Yeah, I don't think that's known. Because, for most classes that you sort of think about every day, either they're going to contain, they're probably going to contain some version of co-enforcing, right? It might not be add omega 1, but it might be add kappa 1 or something, right? And you can run similar arguments for it wherever you are. So, you can be like, you can restrict your class to say all of the forcings that are like this except for co-enforcing, but yeah, I don't know that there's something natural that you can say where this doesn't happen.
Yeah.
Well, but I mean, if you're blending them, like if you have like countably closed, and isn't there some interplay there? Like if you have two different types of things, like co-enforcing and countably closed, like with
Well, you could do like a 2-class version of what Cameron is saying, right? You could be like any two, like I said, any version of add omega 1 always amalgamates with any generic that doesn't add reals or something like that, if you like, right? But maybe that's less satisfying than saying there's a single class so that any 2 generics from that class always amalgamate.
I have a weird question. So I don't know, it just occurred to me, maybe it's dumb. Do you have any feel right now for how properties of, because there's a bunch of posets involved, right? There's the poset of the multiverse structure that you're trying to get, and then the actual forcings that you're using to obtain that. So when you restrict the multiverse to specific types or classes of forcing, or like Heckler forcing or Cohen forcing, do those have like an effect on the multiverse pattern that you would expect to get, like the sort of structure of the multiverse? Like, I don't know, like finiteness that comes up and what you can achieve with Cohen extensions, or I don't know.
Well, so all of our results that I talked about here essentially seem to say that if you restrict to Cohen posets, or if you restrict to wide posets, or if you restrict to Heckler, or if you restrict to this filter-based Matthias thing, everything is in some sense, as complicated as possible, right? I guess that doesn't quite tell you that the structures of the generic multiverses are isomorphic as posets. Maybe that would be an interesting question, right? Like, is the Cohen multiverse isomorphic to the whatever Heckler multiverse or something like that? Or, that might be an interesting way to interpret your question. But at least in terms of the tools that I talked about today, it seems like whenever you can do any kind of coding, you can do as much coding as you want, and you're going to get like as complicated as a structure as you can.
Okay.
Oh,
Any
sorry,
other?
I thought I was unmuted. I was talking to myself. Does anyone have any questions? Okay, Miha, thanks again. Great talk. A nice way to close out the semester.